Hi friends, welcome back to the session. So now we'll be dealing with problem number 3 on thick cylinders. So once again, slightly a different problem when compared to the previous two. So let us begin with the video lecture. A thick cylindrical vessel is 250 mm in internal diameter and has a 50 mm thick wall. It is subjected to an internal pressure of 10 MPa megapascal due to the movement of the fluid. Find the maximum hoop stress developed in the cylinder and also calculate the radial and hoop stress at a point 20 mm from the inner surface. Sketch the variation. Right, so this is the problem given to us. So first let us write down the given data. So let me start with noting the given things. So what all things are given? He has given a thick cylindrical vessel is 250 mm in internal diameter. So internal diameter is 250 mm. So when internal diameter is 250 mm, what will be the radius? Radius, which is denoted by xi, internal radius will be half of this. So it will be 125 mm. Next, it has 50 mm wall thickness. So wall thickness is 50 mm. Wall thickness is 50 mm. It is subjected to an internal pressure of 10 megapascal. So internal pressure Pi is 10 megapascal. Find the maximum hoop stress developed in the cylinder. Also calculate the radial and hoop stress at a point 20 mm from the inner surface. Fine. So this was the given data. Now let me start with the solution part. So initially we know that d naught, that is outer diameter of the cylinder, is equal to inner diameter plus 2 times thickness, right? Inner diameter plus 2 times the thickness. So therefore outer diameter will be 250 plus 2 into thickness is 50 mm. So therefore d naught will be equal to 350 mm. So this is the first step. When external diameter is 350 mm, what will be the radius, outer radius? It will be half of this 350 divided by 2. So it will be 175 mm. And so these two are the prerequisites required. Without calculating these two, you cannot proceed further. Okay, so when these two are known, now I'll start with the core part of our solution. So I'll be using Lamè's equation. From Lamè's equation, from Lamè's equations, we know that so what is known? P is equal to B divided by x square minus A, and on this side it is sigma C is equal to B divided by x square plus A. Right, so these are the general equations what we have derived from Lamè's equation. Now using the boundary condition, what I can write here? using the boundary conditions. So what are the boundary conditions? There are two boundary conditions. There are two boundary conditions. At P is equal to Pi, X will be equal to Xi. At P is equal to P naught, X will be equal to X naught. So these are the two boundary conditions. If I am using these two boundary conditions, then these two equations, right? So if I am putting the boundary conditions in these equations, what I'll be getting, that is what I need to check. So this equation becomes Pi is equal to B divided by Xi square minus A, right? So I have put the first boundary conditions in this equation. So I got Pi is equal to B divided by Xi square minus A. So what is the value of Pi? Value of Pi given to me in the problem is 10 MPa. So 10 MPa is nothing but 10 Newton per mm square, right? Is equal to B is unknown. Xi, value of Xi is 125. You square it minus A. This you take it as equation number 1. Now similarly, putting the second boundary condition, what we will be getting, P naught will be B divided by X naught square minus A. Right, so this is what I get if you put the second boundary condition. If I put on the values, since the external pressure is not given, outside pressure on the surface of the thick cylinder is not given to me, I should assume it as 0. So this point is important. Whenever he has not given any value, you can take it as 0 is equal to B divided by X naught value I have calculated, it is 175. Square this minus A. This is your equation number 2. Right, now solving equations 1 and 2, we get, so I have already shown you how to solve simultaneous equations in the calculators, right? So once again I'll be showing it to you. Kindly concentrate. Go into the equation mode, two unknowns. So value of a1 from first equation, value of a1 will be 1 divided by 125 square. Value of a2 will be minus 1. Value of c1 will be 10. Value of a2 will be 1 divided by 175 square. Value of b2 is minus 1 and value of c2 is 0. So I am getting the value of b as 319010.416, right? So this is what I am getting here, and value of a is 10.416. 10.416. So once if you get the values of A and B, first let us concentrate on hoop stress. He has asked us to calculate the maximum value of hoop stress. So maximum value of hoop stress will always be at the inner surface. So we have studied it in our last problem. So we know that the maximum value of hoop stress always exists at the inner surface of the cylinder. Therefore, from Lame's equation, sigma Ci is equal to B divided by xi square plus A. This should be equal to sigma C max. At circumferential stress at the inner fiber will always be the maximum circumferential stress. So therefore, sigma C max is given by value of B is known 10 point. Okay, so value of A is 10.416 plus value of B is 319010.416 divided by xi square. What is the value of xi? Value of xi is 125 square. 125 square. Therefore, sigma C max. So let me calculate. I'll reset this. So it is 319010.416 divided by 125 square plus 10.416. So sigma maximum is 30.832. So this value is coming out to be 30.832. 30.832 MPa megapascals. Okay, that is the first thing what he has asked to us in the problem. So thereafter he has asked us to calculate the radial and hoop stress at a point 20 mm from the inner surface. At a point 20 mm from the inner surface. So next I'm writing here radial and circumferential stress at a distance of 20 mm from inner surface. So I'll just draw a rough sketch here, something of this kind. Okay, let us say this is the center. Okay, so this is xi, xo. Now there is a need to calculate the radial stress and the circumferential stress at a distance 20 mm from the inner surface. So let us say I need to calculate this is x. This distance is 20 mm. Right? So you are asked to calculate the radial stress and the circumferential stress on the green layer. So I'll consider this distance as x. I'll consider this distance as x. So x is equal to xi. X is equal to xi plus 20. So x is equal to 125 plus 20, 145 mm. Right now here at x is equal to 145 mm, you need to calculate the circumferential stress and a radial stress. So first I'll be calculating the radial stress. So how you calculate the radial stress? So P at x is equal to 145 mm will be given by B divided by at x is equal to 145 mm square minus A. Same Lame's equation only the value of x is taken as 145 mm. Right? So therefore P at x is equal to 145 will be equal to value of B is 319010.416 divided by value of x to be taken as 145 square minus 10.416. So this if you solve, what you'll be getting? So this is the value of radial pressure. So value of radial stress or radial pressure will be 319010.416 divided by 145 square minus 10.416. So that value I am getting it as 4.756. So this value is 4.756 MPa. Right. So the last part which is left out is calculation of hoop stress at x is equal to 145 mm. So at last I need to calculate sigma c at x is equal to 145 mm. Okay, so that is given by b divided by x at 145 mm. Need to square this plus a. So this is the formula, same the Lame's equation what we have used previously. So therefore sigma c at x is equal to 145 mm will be equal to value of b is 319010.416 divided by 145 square, value of a is 10.416. So therefore sigma c at x is equal to 145 mm or at a distance of 20 mm from internal diameter, which is same. So let me check out what I'll be getting here. 319010.416 divided by 145 square plus 10.416. So it is 25.58 MPa. 25.58 MPa. Right, so now let us draw the variation. So in order to draw the variation, let me draw the variation. So in order to draw the variation, you need to show the inner and outer surface of the thick cylinder. So I'll show the inner surface and also show the outer surface. So after showing inner and outer surface, let me draw a reference line. So that which I can consider as my zero line. Above that things will be positive, below that things will be negative. Right. So let me draw a reference line. Okay. Now this is inner surface, outer surface. Your center will be somewhere over here. I have not shown it. Right. Now you need to show the values. First, I'll be marking the circumferential stresses or hoop stresses. So, what is sigma Ci? Sigma Ci is 30.83. 30.83 is the value of sigma Ci. So, first I'll mark that. So, let us say I'll mark it here. So, this is sigma Ci. Next, so let me write it. So this point is sigma Ci, sigma Ci 30.83 MPa, right? Then second point to be marked is sigma C naught on the outer layer. On the outer layer, I need to mark sigma C naught, sigma C naught on the outer layer. So value of sigma C naught is coming as 20.832. So let us say it is somewhere over here, 20.832. So it is sigma C naught 20.832 MPa. Next I'll mark internal pressure. Value of internal pressure Pi. Value of internal pressure Pi is 10 MPa. Right. So let me mark it here, 10 MPa, somewhere over here. So this is Pi 10 MPa. P naught is not given to me in the problem, so I need to take it as 0. So this is the reference line. Exactly on the reference line, I'll take it as 0. So this point is P naught is equal to 0 MPa. So then you need to join these. So I'll just join these. Okay, so the values here, just go on marking the stresses. Later I'll be showing the directions. Okay, from the reference line here on the downside things are negative, and above these are positive. So on top of reference line everything is positive, and below the reference line everything is negative, right? So these two are the circumferential hoop stresses, and these two are the radial stresses, right? So I hope things are clear. So that's it for today's session. Have a great day. Take care. Bye bye.